Dr. R. Hemavati is an assistant professor in mathematics in Queen Mary's, Chennai. She has specialized on functional analysis. Having 12 years of experience in teaching, she has won various awards for her performance. She has published papers in 14 international journals, 3 national journals, and has presented papers in 10 international and in 5 national conferences. She is also one of the editors for an international journal.
Welcome to UGC lecture series. In this session, we are going to deal with continuous distributions. In the earlier sessions, we have dealt with probability functions, probability mass function, probability density functions and discrete distributions. Whereas the discrete distributions dealt with random variables which are discrete in the sense countable and finite. Now, continuous distribution is going to deal with continuous random variable, wherein the values of continuous random variables will be continuous in the sense it will be taking the values in interval. Any particular random variable, if it takes values in an interval, then it is called continuous random variables. We have dealt with these kind of discussions earlier. Now, following the continuous random variable, we are going to deal with its probability distributions, some special probability distributions. Continuing in line with the distributions, earlier discrete was dealt. Now, in this episode, we are going to deal with continuous probability distributions. In particular, normal distribution is dealt elaborately by discussing its probability density function, moment generating function. To learn more about normal distribution, some more examples are also worked out in this session. So, continuous distributions. What are the various continuous distributions you are going to deal with? They are normal distribution, uniform distribution, exponential distribution, beta distribution and gamma distribution. In the discrete distributions, we have dealt with binomial distribution, Poisson distribution, hypergeometric distribution, negative binomial distribution and geometric distribution. There are various distributions, but these are in particular of importance. So, in continuous distributions also there are various distributions, but in particular these 5 distributions are playing a very important role. So, first of all we shall deal with normal distributions, then we will deal with the other distributions one by one. What is the probability density function of normal distribution? Whenever we say a random variable will be following a particular function. That particular function, if the random variable is discrete, then the particular function will be called as probability mass function. If the random variable is continuous, it will be called as probability density function. These were already dealt. So, normal distribution being a continuous distribution, it will be having only probability density function. Okay. So, a continuous random variable is said to follow a normal distribution, otherwise Gaussian distribution with parameters mu and sigma. This mu and sigma are called mean and standard deviation. If its probability density function is given by f of x is equal to 1 by sigma root of 2 pi e power minus x minus mu whole square by 2 sigma square. This is the function. Okay. So, what are the values? Various values of x will take. As already told, continuous random variable will be taking the values only in an interval. Okay. So, this is the probability density function of a normal distribution, otherwise called as Gaussian distribution. This Gaussian distribution plays a very important role in random processes. Random processes is the random moment associated with the time t. Okay. In electronics, it plays a very important role. Next, probability density function of standard normal distribution. The standard normal distribution n of 0, 1 is called a standardized or standard normal distribution whose density function is given by. That is, in the previous slide as we discussed its normal distribution, we simply write that when x follows a normal distribution, we write it as n of x following normal distribution with mu comma sigma. These mu and sigma are parameters. This normal distribution n of 0, 1 means x is following a normal distribution with mu and sigma. To change the variable, we have to deal with another random variable, that is we say z is following a normal distribution with parameter 0, 1. It means the mu is taking the value 0 and sigma is taking the value 1. This is the concept of standard normal distribution. A standard normal distribution is nothing but a normal distribution whose mean is 0 and standard deviation is 1. So, accordingly, how the density function will change? Density function already discussed, it was f of x is equal to 1 by sigma root of 2 pi e power minus x minus mu by mu whole square by 2 sigma square. In this function, you substitute the values mu is equal to 0 and sigma is equal to 1. So, accordingly, your normal distribution will have the density function f of z. Since you should change the function, we shall have another name as pi of z. So, we shall have the density function of normal distribution, wherein we have substituted the values mu is equal to 0 and sigma is equal to 1 in the normal distribution. So, accordingly, you will have 1 by root of 2 pi e power minus z square by 2, and z will be having the values same, minus infinity, less than z, less than infinity. So, this is the probability density function of standard normal distribution. We are going to deal with the examples in normal distribution only by converting the problems to standard normal distribution. So, this is very important. There are many characteristics of normal distribution. In particular, we will deal with the two characteristics only, so that it will be useful for us to do problems. The curve is bell shaped and is symmetrical about the line x is equal to mu. What does it mean? As already you know, the normal distribution curve is always a bell shaped. This you would have dealt in your earlier study. This is a normal distribution curve and it is symmetrical about the line x is equal to mu. Usually when the x axis and y axis intersect, x axis and y axis intersect, it will be called as the origin, but here it is not the origin. The x axis and y axis meet at the line x is equal to mu. Okay, so, it is symmetrical about the line x is equal to mu, that is the total area covered by the curve and the lines are divided as two parts equally. Okay. So, as we know, the total probability is 1. So, the whole total area is 1 and it is this particular part, the area is 0.5 and this particular part, whereas the divided area, this is 0.5. So, that you get the total area as 1 and this particular curve is asymptotic and it never touches the x axis line. So, continuing with the characteristics of normal distribution, next mean, median, mode of the distribution coincide. That is mean of the normal distribution, we started with the definition itself is mu, and similarly standard deviation of the normal distribution is denoted by sigma. Usually when we deal with the distributions, we will first find out the moment generating function, and using moment generating function we will find out the mean and standard deviation. But in this normal distribution, we started with the parameters mu and sigma, which are called the mean and standard deviation. So, the mean, median and mode of the distribution coincide. It means mean is also mu, median and mode of the distribution is also mu. First find out the moment generating function of a standard normal distribution, and using the shifting property we will find out the normal distributions MGF. Then first we will find out moment generating function of a standard normal distribution. What is the PDF of standard normal distribution? It is 1 by root of 2 pi e power minus z square by 2. In continuation with the moment generating functions of the earlier distributions we have dealt, first of all we have to define what is a moment generating function. M x of t is equal to expectation of e power t x. But here a standard normal distribution, variable is denoted as z, therefore, we have to denote it as mz of t is equal to expectation of e power tz. Being a continuous distribution, using the expectation, it is z is equal to minus infinity to z is equal to plus infinity e power tz f of z dz. Here in the place of f of z, we should use pi of z, because pi of z is the PDF of standard normal distribution. This is equal to integral minus infinity to infinity e power tz 1 by root of 2 pi e power minus z square by 2 into dz. We will find out the moment generating function of standard normal distribution. This is equal to 1 by root of 2 pi. This e power tz and e power minus z square by 2 dz is clubbed as minus infinity to infinity e power minus 1 by 2 z square minus 2 tz dz. Completing the squares of z square minus 2 tz 1 by root of 2 pi integral minus infinity to infinity e power minus 1 by 2. To complete, you should add and subtract t square minus t square dz. These three constitute a square, that is a minus b whole square, that is z minus t whole square, minus infinity to infinity e power minus 1 by 2 z minus t whole square, and this particular thing is taken outside as e power t square by 2 dz. Okay. So, this is e power t square by 2 by root of 2 pi integral minus infinity to infinity e power minus z minus t by root 2 whole square dz. You substitute u is equal to z minus t by root 2 and accordingly change, you will get is equal to e power t square by 2 by root of 2 pi integral minus infinity to infinity e power minus u square into du is equal to 1 by root 2 dz. Therefore, root 2 into du. Again substituting this u square, this root 2 in fact is getting cancelled, root 2 particularly it will get cancelled. Again continuing this, minus infinity to infinity e power minus u square du is nothing but gamma half is equal to e power t square by 2 root pi, and that particular integral is gamma half, where you have the value of gamma half as root pi. Okay. So, this is equal to e power t square by 2 by root pi into root pi gets cancelled. So, m z of t is equal to e power t square by 2. This is the moment generating function of a standard normal distribution. So, next we have to write down the moment generating function of a normal distribution. What is the relation between normal distribution and standard normal distribution? That is z is standard normal variable, x is normal variable, and it is related by the relation z is equal to x minus mu by sigma, and we know that m z of t is equal to e power t square by 2. So, what is m x of t, which is the moment generating function of a normal distribution? You have to derive x from this, cross multiplying x is equal to mu plus z sigma. So, m x of t is equal to m mu plus z sigma of t. This is e power mu t into m z of sigma t. So, what is the m z of t? M z of t is e power t square by 2. So, what will be m z of sigma t? That will be e power, in the place of t you are having sigma t. So, sigma t whole square by 2. So, that is e power mu t plus sigma square t square by 2. This is the moment generating function of normal distribution. Using this moment generating function of normal distribution, we shall now derive the central moments of normal distribution. Central moments means mu 1, mu 2, mu 3 and mu 4. That is mu 1 is always 0, mu 2 represents the variance and mu 3 represents third central moment, mu 4 is fourth central moment. So, first of all we shall derive mu 1 dash, mu 2 dash, mu 3 dash and mu 4 dash. That is mu 1 dash is mean, mu 2 dash is second raw moment, mu 3 dash and mu 4 dash are third and fourth raw moments. As I discussed, first we shall find out mu 1 dash. Mu 1 dash is expectation of x. Expectation of x is coefficient of t by 1 factorial in the expansion of mx of t, where what is mx of t we have found out is equal to e power mu t plus sigma square t square by 2. We shall expand this using the exponential definition. 1 plus mu t plus sigma square t square by 2 plus mu t plus sigma square t square by 2 whole square by 2 factorial plus etc. Accordingly, what is the coefficient of therefore, coefficient of t by 1 factorial is coefficient of t is only mu. So, E of x is equal to mu, and the expectation of x square is equal to coefficient of t square by 2 factorial in the expansion of mx of t. What are the t square by 2 factorial coefficient? This one, sigma square and plus mu square, is not it? Sigma square plus mu square. We want the coefficient of t square by 2 factorial itself. T square by 2 factorial is this particular part. So, its coefficient is sigma square. Similarly, here if we expand using a plus b whole square, it is mu square t square plus etc. by 2 factorial. So, t square by 2 factorial coefficient will be mu square. This is E of x square, right. And similarly, what is expectation of x cube? This is equal to coefficient of t cube by 3 factorial in mx of t, that is 3 mu sigma square plus mu cube. Similarly, expectation of x power 4 is coefficient of t power 4 by 4 factorial in mx of t, and that gives you 3 sigma power 4 plus 6 mu square sigma square plus mu power 4. So, using this, what are the central moments of a normal distribution? This is mu 1 is always 0, mu 2 is using the relation mu 2 is equal to mu 2 dash minus mu 1 dash square, that is equal to mu 2 dash is expectation of x square, this is your mu 2 dash, right. This is mu 3 dash and this is mu 4 dash. So, mu 2 dash is sigma square plus mu square minus mu 1 dash is E of x, this is mu 1 dash is mu and this whole square. So, sigma square plus mu square minus mu square is sigma square. Okay. So, similarly, we will have mu 3 is 0 and mu 4 is equal to 3 sigma power 4. These relation are already dealt with. You can use the relation between raw moments and central moments and work out the mu 3 as 0 and mu 4 as 3 sigma power 4, wherein we need only mu 2 as a sigma square. As I already told you, we started with the definition of normal distribution with the definition that its mean is mu and variance is say standard deviation is sigma. So, we have derived mean is mu and variance is sigma square, and hence standard deviation is sigma. We shall do some problems in normal distribution. It is known from the past experience that the number of telephone calls made daily in a certain locality between 3 p.m. and 4 p.m. has a mean of 352 and standard deviation of 31. What percentage of times will there be more than 400 telephone calls made in this locality between 3 p.m. and 4 p.m. This particular problem is taken from a telephone exchange. For doing a problems in normal distribution, first of all we need the parameters. The parameters are mu and sigma, and the parameter value mu is 352 and standard deviation is 31. Percentage of times means you are asked to find out the probability where there will be more than 400 telephone calls. As I already discussed, we have to use the characteristics of normal distribution based on the area. All probability values are nothing but area under the normal curve and x axis. Okay. So, for finding the probability values in normal distribution, we have to use the standard normal distribution table. You can refer the table available in many books or in the net also, internet also. Okay. So, in particular now I will use the values from the standard normal distribution table to work out this problem. Use the value of mean and standard deviation, convert the problem to standard normal distribution problem, use the tables of standard normal distribution table, work out the values and find out the percentage of times. Okay. In particular, normal distribution is called Gaussian distribution, and it deals with the time process. So, particularly we have taken a time problem where we need a percentage of 400 more telephone calls between a particular interval of time. Interval of time is 3 p.m. and 4 p.m. First of all, we have to start with the given values. Given mu is equal to 352 and the standard deviation is equal to 31. We know that the standard normal distribution value is given by z is equal to x minus mu by sigma, that is x minus 352 by 31. Okay. Usually the values in the problem will be given in terms of normal distribution only. We only have to convert it to standard normal distribution. What is the probability asked? Probability asked is p of x greater than 400, percentage more than 400 telephone calls between 3 p.m. and 4 p.m. This 3 p.m. and 4 p.m. this particular 3 and 4 we are not going to use it anywhere. It is only representing the interval of time. If x is equal to 400, what happens to the z value? Z is equal to 400 minus 352 by 31. And this particular value is given, find out to be 1.55. So, x is equal to 400 implies z is equal to 1.55. So, x greater than 400 will be implied as z greater than 1.55. So, what is the probability of x greater than 400? This implies probability of z greater than 1.55. All the problems in normal distribution we have to use this bell shaped curve where we have to plot z is equal to 1.55. It is positive because this particular value is x is equal to mu and it represents z is equal to 0. So, to the right is positive z values and to the left of this asymptote is negative z values. So, just draw a line on z is equal to 1.55. Greater area is represented by this shaded part and we need this area. Okay. Whereas, your standard normal distribution will give you only the area from z is equal to a particular value. From the tables I have quoted the area as z from z to 1.55. From the tables it is 0.4394. This is from the normal distribution tables. Okay. This is represented from by the value 1.55. Usually it will give only the values from 0 is 0.4394. Okay. So, we want this shaded part, we know that half of the area is 0.5 and this particular area is 0.4394. So, what will be this shaded area? The shaded area is 0.5 minus 0.4394. So, this particular value is taken from tables 0.4394. So, 0.5 minus 0.4394 is 0.0606. Percentage of times that 400 more telephone calls will be received from 3 p.m. to 4 p.m. is 6.06 percentage. This is how we should work out the problems in normal distribution. In this session, we have dealt with continuous distributions. Continuous distribution, starting with we have dealt with normal distribution, normal distributions probability density function, and we using normal distribution, standard normal distribution was discussed. Then moment generating function of normal distribution was discussed, and moment generating function, using moment generating function of normal distribution, we have derived the central moments of normal distribution, and a problem was discussed in this session. Thank you.